now let's utilize the second condition regarding the cross section, and this information would give us information on the maximum shear stress sigma x. So the logical flow is as follows. So we are considering the g-axis is coming out of this plane, and you have y here, you have x here, and we have applied the moment m. So what we want to satisfy is, suppose that for each y position we have infinitesimal force dF, okay, and because we are taking the right hand rule, y multiplied by dF considered to be minus dmg, okay. So the if you consider y multiplied with dF, it's clockwise rotation, which is opposite sign in terms of right hand rule when we consider g-axis is coming out of this plane, okay. So dmg can be considered as y df. And what about df? Df can be obtained from sigma y, not sigma y, sigma x as a function of y, and dA, and sigma x as a function of y can be written as minus y over c sigma x max dA. Okay, so if you plug in the expression for dF here, okay, then we have y here, we have negative sign and sigma x max and c, and this ends up becoming this expression. dmg for infinitesimal area can be written as this, and if you integrate this infinitesimal mg over the entire cross section, it must be same as applied moment m. Okay, now so here you have minus sign, you have a minus sign, these minus sign cancel out, and this is why you don't have a minus sign here. So if you massage this equation, plug in this dmg into the place over here, and you have y squared c and sigma x max, and these two are constant values, so we take them out of this integral. Then we end up having this interesting expression, integral y squared dA over the entire cross section, and we define this as area moment of inertia. Then after defining this integral as I, we end up having m equals to be sigma x max divided by c multiplied by I. Now you can obtain sigma x max in terms of applied moment m, and the geometrical values c and I. C is the largest distance from the neutral axis. It can be either top plane or bottom plane depending on the geometry. Okay, now let's plug this expression. Now we have information regarding sigma x max in terms of m and geometry. If you plug this into the position of sigma x max, if you plug in cm over I here, you end up having sigma x as a function of y can be written as minus y divided by I multiplied by m. We call this as flexure formula. Okay, and flexure formula tells the relationship between applied moment, position, and geometrical value, which is area moment of inertia, and the stress distribution in terms of y. Okay, and if you also consider the maximum normal strain and maximum normal stress relationship, and what you can obtain is, if you plug in these expression, and if you also consider E times epsilon x equals to be sigma x, you end up having the relationship between applied moment m and the radius of curvature, radius of bending rho, and Young's modulus, and area moment of inertia. Okay, so now we begin from like an unknown value of rho, okay, unknown value of epsilon max, right, because we don't know rho. But after going through this mechanical equilibrium equation, we prove that neutral axis go through centroid under the pure bending. It is really important that neutral axis go through centroid under the pure bending. If we don't have the constraint on pure bending, we cannot say actually neutral axis does not go through the centroid. That's the first lesson. And from the second lesson, from the second condition, the second lesson we're gonna get is we finally connect the relationship between applied moment and the geometry, and applied moment and strain and stress distribution. Okay, so these are what we can obtain from mechanical equilibrium analysis, starting from the geometrical assumptions in second topic of today's lecture. So what's the implication in terms of design? In terms of design, we have to satisfy the maximum normal stress must be smaller than allowable stress of the material. And if we take a look at closer look at the sigma x max, it can be written as c times m divided by I. And if we define S as the section modulus I over C, you can write down maximum normal stress can be written as M over S. So when S is large, given same moment, you're gonna have smaller maximum stress. Okay, so yeah, you'd better have a cross section with high section modulus. Okay, and what does it mean to have a high section modulus? Given same area, you have to increase I, you have to decrease C. Okay, that's how you reduce the maximum stress for reliable mechanical design. And interesting thing here is sigma x max depends solely on cross-sectional geometry. Okay, so you can see that when you look at sigma x max, yeah, this is applied moment. This is the information about cross-sectional area, cross-sectional shape, and this is about the distance from the neutral axis. There is no information of material. Okay, so the implication here is whether you consider rubber or steel, whether you have rubber beam of this side, whether you have steel beam with exactly same size, and if we apply exactly same moment M, yeah, whether you consider rubber or steel, the maximum stress is the same. Okay, so because when they have exactly same geometry. Okay, however, we cannot say that it's identical deformation, because there is of course difference between rubber and steel. The difference is they deform differently. Okay, even though their maximum stress is identical, if we consider maximum strain must be maximum stress divided by Young's modulus, and Young's modulus of steel is orders of magnitude larger than rubber, and the steel deforms much less than rubber, even though we apply same moment, even though we apply same stress distribution. Okay, so this is something you have to remember. And actually, same conclusion is true for axial loading and torsion. Okay, if you consider stress distribution, yeah, you can see that there is no information about material. Okay, so the stress distribution is identical if geometry is the same. However, even though the stress is the same, because they have different they have different Young's modulus, they have different shear modulus, their deformation would be different if elastic constants are different. Okay, so this is the implication of this deformation and stress analysis. Now let's move on to the like a realistic engineering example. So first example we're gonna consider is very simple cross section. The cross section with rectangular shape, and suppose that the width is b and height is h. Okay, and if we obtain the area moment of inertia I in terms of the entire cross section, it can be written as this. Okay, so we have to do y squared dA integral from negative h over 2, positive h over 2, and here dA can be written as b times dy. Okay, so this is our dA. Okay, so this is our dA, and we do this integral from minus h over 2 to h over 2. Oh, I think it can be confusing, so let me just say cross section here. After we replace dA with bdy, and then we can use this range. Okay, then after we perform this integral, we found out that I is 1/12 bh cube, and if we identify that bh is a, it can be written as 1/12 ah square. Okay, so the implication is, even though two cross sections have same areas A, if their height is different, we're gonna have different I. Okay, so if we compare two cross section with the neutral axis here, neutral axis here, what you can see here is, because even though they have same cross sectional area, the height of H1 I1 sample 1 and height of sample 2, the H1 is much larger than H2 and I1 will be much larger than I2 because I is proportional to H square. Okay, so this is the best way to utilize the same material if we consider like a same mass and same weight, and if we want to minimize the bending, we'd better increase the height and increase the width B if the A is given as same. And there is even better way, given same cross-section area, if we place more and more material at the top and more material at the bottom, where we're gonna have largest stress, we can utilize the material's resistance in full capacity. Okay, so by doing so, because you are increasing like a more material density at like a higher absolute y values, and this will increase area moment I. Because area moment I increases, you're gonna have smaller deformation due to higher resistance to bending bending moment M. Okay, and actually you can see the implication of this in many construction sites. Okay, so when you take a look at the I-beam structures, when you are looking at the construction site, I-beams always oriented in this way. You never seen I-beam oriented in this way because I-beams is designed to hold the gravity here, and this I-beam must be resistance to the bending here or bending there. Okay, so to sustain bending in vertical direction, resist bending in vertical direction, we have to orient I-beam in this way instead of that way. Okay, and you can find this example in a lot of construction sites. And if you happen to find any construction site nearby, please visit the construction site and check the orientation of I-beam and think about what we have learned in first lecture on bending chapter. Okay, so with that, let me close today's lecture.